Welcome to another module in this massive open online course on probability and random variables for wireless communication. So, in the previous module we have looked at Bayes' theorem. Let us now look at an application of Bayes' theorem in the context of digital communication systems and wireless communications. As we said, this is a course on applied probability theory. So, we have looked at Bayes' theorem. Let us look at an important application of this in the context of wireless communication. So, what we are going to look at today is known as the map receiver, and this acronym MAP stands for maximum a posteriori So, the acronym MAP stands for maximum a posteriori probability, or basically the MAP receiver. This is a very important receiver in the context of wireless communication or even a traditional digital communication, that is digital information symbol based communication system. This MAP receiver, which computes the a posteriori probabilities that we had illustrated previously in the context of Bayes' theorem. So, let us now consider a digital communication system with binary information symbols in which the sample space is S, consisting of the binary information symbols 0 and 1. So, let us consider a digital communication system or a digital communication link based wireless communication system in which the sample space consists of the binary information symbols. So, this is my sample space and these are my binary this is the sample space and these are the binary information, this is the sample space and these are the binary information symbols. Therefore, now, so binary information symbols are 0 and 1 and the sample space contains these two binary information symbols 0 and 1. Now, let us consider the events A0 equal to 0 and this is a very simple example. So, there are two events A0 equal to 0, A1 equal to 1, that is A0 corresponds to the binary symbol 0 and A1 corresponds to the binary symbol A1 corresponds to the binary symbol 1. So, there are two binary symbols A0 0 and 1. A0 corresponds to the event of the transmitted binary symbol being 0, A1 corresponds to the event of the transmitted binary symbol being 1. And therefore, now you can clearly see that A0 and A1 are mutually exclusive and exhaustive because A0 union A1 equals 0 union 1, which is basically equal to 0 comma 1, which is the entire sample space S. So, A0 union A1 equals S. So, A0 union A1 is equal to the entire sample space because A0 is 0, A1 is 1, their union is the set 0 comma 1, which is the entire sample space. And further, A0 and A1 are clearly mutually exclusive because A0 intersection A1 is the null event phi. You can see A0, again it is not difficult to see that A0 intersection A1 equals phi, which is our null event or our empty event. Therefore, A0 union A1 is equal to S and A0 intersection A1 is equal to phi, which implies A0 comma A1 are mutually exclusive and exhaustive. So, A0 and A1 are therefore for this binary information symbol based digital or wireless communication system, A0 and A1 are mutually exclusive and exhaustive. So, therefore, this satisfies one of the prerequisite conditions for our Bayes theorem. Remember, for our Bayes theorem we said whatever are these sets A0 and A1, these have to be mutually exclusive, that is their intersection has to be the null event, and they have to be exhaustive, that is the union of these has to be the entire sample space S. So, this satisfies the prerequisite for the Bayes theorem. Now, let us look at the application in the context of this in the context of communication. We consider what is known as a binary symmetric channel. Let us consider a standard channel in communication. This is a binary symmetric, this is what is known as a binary symmetric channel, and this can be described as follows. This is, I am showing a schematic representation of a binary symmetric channel, where I can have the left side is the transmitter and the right side is the receiver. I can transmit either a 0 or 1, that is A0, as we had seen before, A0 corresponds to the event 0, A1 corresponds to the event that the transmitted symbol is 1. Let us say the probability of A0 P0 equals 0.1, the probability of A1 P1 equals 0.9. So, we have a binary symmetric channel in which I have the transmitter side and I have the receiver side. At the transmitter side, I can say, I am saying that we can transmit a symbol that is A0, or we can transmit a A0 that is the symbol 0, that is the event A0 corresponds to the transmission of the symbol 0, event A1 corresponds to the transmission of the symbol 1, and we are also saying that the probability of A0 is 0.1, that is the probability of that symbol 0 is transmitted is 0.1, probability that the symbol 1 is transmitted, that is probability of A1, which is equal to P1 is equal to 0.9. Therefore, probability of A0 equals, we are denoting by P0 is equal to 0.1, probability of A1 is equal to P1, which is equal to 0.9. Further, at the receiver also we can have 0, that is the event B which corresponds to receiving 0, or the event B tilde which corresponds to receiving 1. Further, a transmitted 0 can either be received as a 0, the probability of which is equal to 0.8, which is equal to 1 minus P, or the probability of a 0 can get flipped to 1, the probability of which is P equal to 0.2. So, therefore, we are saying this is an interesting scenario where a transmitted 0 can either be received as a 0 with probability 0.8, or the transmitted 0 can be flipped to a 1, that is there is an error which occurs on the channel, due to which the 0 that is transmitted gets flipped to a 1, and the probability of this happening is 0.2. Similarly, the 1 that is transmitted can either be received as a 1, the probability corresponding to which is 0.8, which is equal to 1 minus P, or it can get flipped to a 0, the probability of which is happening is P equals 0.2. So, these two links, these two things that we show here, these corresponds to the flipping. What do we mean by flipping? That is, a 1 gets flipped to a 0 or a 0 gets flipped to a 1 because of errors on the channel, and this channel is known as a binary symmetric channel. A binary channel basically because it represents binary information symbols 0 and 1, which are transmitted as 0 and 1 and can be received as either 0 or 1, and symmetric because these different probabilities are symmetric between 0 and 1. The probability that a 0 can get flipped to a 1 and the probability that a 1 can get flipped to a 0, both these probabilities are symmetric and these probabilities are equal to 0.2. Therefore, this is known as a binary symmetric channel. This is a very important channel that is used to model the transmission of digital information symbols across both a digital communication channel and also a wireless communication channel. A wireless communication channel which uses digital symbols, of course, is also based, is a special case of a digital communication system. So this is a binary symmetric channel which is used to model transmission of binary information symbols over a communication channel. And let us now look at this. So what we have given is, we have given that the probability of A naught, that is the probability that the transmitted symbol is 0, is 0.1. The probability of A1, which is equal to P1, which is equal to 0.9, is basically the probability that the transmitted symbol is 1. And as we had said before, these are the prior probabilities. So these here, these are the prior. I hope everyone remembers from the previous module, these are the prior probabilities. These are the prior probabilities. And the probability, now also observe the probability of flipping, that is the probability of B given A naught, the probability of B given A1, which is equal to the probability B given A1 is probability received symbol is 0 given transmitted symbol is 1, which is equal to the probability of B tilde given A0, that is the probability that received symbol is 1 given transmitted symbol is 0, and these are the flipping probabilities which are 0.2, and probability of B given A naught equals probability of B tilde given A1. These are the non-flipping probabilities, that is the probability that a 0 is received as a 0 and 1 is received as a 1. These are non-flipping probabilities. These are known as, these conditional probabilities, these are known as the likelihoods, as we had derived, as we had described in the previous module. These probabilities, these are known as the likelihoods. So we are given the prior probabilities, we are given the likelihoods. Now we would like to employ, Bayes theorem to consider to compute the a posteriori probabilities. What is the a posteriori probability? We would like to compute what is the probability of, A naught given B. Remember, this is the a posteriori. This is the a posteriori probability. This is the a posteriori probability. Remember, what is the a posteriori probability P of A naught given B? That corresponds to the probability A naught is the event, remember, corresponding to the transmission of 0, and B is the event corresponding to the reception of 0. Therefore, P A naught given B corresponds to the probability that the 0 has been transmitted given that a 0 has been received. So what we are asking is the question, what is the probability, or what we are asking is, given that given B equal to 0 has been received, what is the probability, A naught equal to 0 has been that is, given that 0 has been received, what is the probability that the actual transmitted symbol is a 0. That is the question that we are asking. What is the probability of A naught given B? That is the a posteriori probability of A naught given B. And now let us compute this. We know that the a posteriori probability of P of A naught given B, the a posteriori probability of P of A naught given B, we know from Bayes theorem that this is equal to the probability of B given A naught times the probability of A naught divided by the probability of B given A naught into probability of A naught plus probability B given A1 into probability of A1. And now if we substitute these quantities, we know that the probability of B, let us go back and take a glimpse at this channel. Probability of B given A naught we know is the probability 0 is received corresponding to 0 transmitted, that is 0.8, and these various values are given. The prior probabilities, probability of A naught is 0.1, probability of A1 is 0.9 and so on. So these values are given. Now all we have to do is substitute these values in the Bayes theorem, and this can be calculated as probability of B given A naught, that is 0.8, into probability of A naught, that is 0.1, divided by probability of B given A naught 0.8 into probability of A naught 0.1 plus probability of B given A1. This is the flipping probability, probability of 0 given 1 has been transmitted, that is 0.2 times probability of A1, the prior probability of A1, that is 0.9. Therefore, this is equal to 0.08 divided by 0.26, that is equal to 8 divided by 26. So the probability, the a posteriori probability of A naught, the a posteriori probability of A naught given B is equal to 8 divided by 26. What we have seen is we have calculated using Bayes theorem, we have calculated the a posteriori probability of A naught given B, that is what is the probability that a 0 has been transmitted given that a 0 has been received at the receiver. Now let us compute the other a posteriori probability. What is the probability that a 1 has been transmitted given that a 0 has been received, and this can be calculated as the probability of A1 given B, which is equal to probability of B given A1 times probability of A1 divided by probability of B given A naught divided by probability of A naught, probability of B given A1 times probability of A1, which is equal to probability of B given A naught divide B given A1 is again the flipping probability 0.2 times probability of A1, which is 0.9, divided by probability of B given A naught, which is 0.8 times the probability of A1, which is 0.1, plus probability of B given A1, which is 0.2 times probability of A1, which is 0.9, and therefore this is equal to, again you can see 0.18 divided by 0.26 equals 18 divided by 26. And now you can observe, if you look at these two quantities, the probability of A1 given B and the probability of A. Now if you look at these two quantities, the probability of A not given B, that is the probability corresponding to transmission of 0 given a 0 has been observed, and probability of A1 given B, there is a probability corresponding to transmission of 1 given 0 has been observed. Very interestingly, you observe that the probability of A1 given B, which is 18 by 26, is higher than the probability of A naught given B, that is 8 by 26. So what you observe, that is something very fascinating. What you observe is that probability or the posterior probability of A1 given B, which is equal to 18 by 26, is greater than 8 by 26, which is the posterior probability of A naught given B. right. So, we have basically what is this? This is the posterior probability corresponding to, this is the what is this? This is the posterior probability or a posteriori, let us write it as the a posteriori probability corresponding to 1, and this is the a posteriori probability corresponding, this is the a posteriori probability corresponding to 0. And what we are saying is the a posteriori probability, even though a 0 has been received, the a posteriori probability corresponding to the transmission of 1 is higher than the a posteriori probability corresponding to the transmission of 0. Therefore, based on this at the receiver, even though we are observing 0, that is the event B which corresponds to the reception of 0, we conclude that the actual transmitted symbol must have been 1 with a higher probability than 0. So, based on maximum a so based on this computation, based on this we choose or basically decide or detect 1 at the receiver, since it corresponds to the maximum a posteriori probability, and this receiver is therefore known as the maximum a posteriori probability receiver. That is, corresponding to the observation, we compute what are the a posteriori probabilities of the various transmitted symbol, and we choose that transmitted symbol which has the maximum a posteriori probability, and this is known as the maximum a posteriori probability receiver. That is, even though we observe a symbol 0, we compute the a posteriori probability corresponding to the transmission of 0, we compute the a posteriori probability corresponding to the transmission of 1, and we conclude that the transmission of 1 has a greater a posteriori probability. Therefore, we decide as the 1 has been transmitted by the transmitter. This is known as the maximum a posteriori probability receiver or the MAP receiver, and this minimizes the probability of error at the receiver. This is the optimal receiver which minimizes the probability of error at the receiver. So, this is known as the MAP receiver. This principle is known as the MAP principle. This is a very important principle in the context of communication systems. This is known as the MAP. This is known as the MAP or the maximum a posteriori probability principle, and this leads to minimizes the probability of error. This minimizes the probability of error. This minimizes the probability of error at the receiver. The MAP receiver minimizes the probability of error at the receiver. Therefore, this MAP receiver, which is built on the principle of the Bayes theorem, which computes the a posteriori probabilities of the various transmitted symbols and chooses the transmitted symbol which has the maximum a posteriori probability, is known as the MAP receiver. Alright. So, the MAP receiver is a very important. Now, on the other hand, if you look at a simple maximum likelihood receiver, now if you look at the likelihoods, what are the different likelihoods? If you look at the likelihoods, the likelihood of B given A naught is 0.8 and max likelihood of B given A1 is 0.2. So now if you look at the likelihood, simply if you look at the likelihoods, probability of A naught given, that is the probability of B, that is received observation 0 corresponding to transmission of 0 equals 0.8, probability of B given A1 equals 0.2. This is the flipping probability, and these are the likelihoods. And based simply on the likelihood, we can see that A naught has a, because the probability of B given A naught is higher than the probability of B given A1, we can see that A naught, or the transmission of 0, has a higher likelihood. Therefore, if we decide based on this, if we decide that a transmitted symbol is 0, this is known as the maximum likelihood receiver. So maximum likelihood receiver, so therefore likelihood, we are saying that P of B given A naught is greater than, or we are saying that if I have to write it clearly, P of B given A naught, which is equal to 0.8, is greater than 0.2, which is equal to P of B given A1. Therefore likelihood of 0, not the a posteriori probability, likelihood of 0 is greater than likelihood of the binary information symbol 1. Therefore maximum likelihood receiver, therefore maximum likelihood the maximum likelihood or ML receiver decides 0. So the maximum likelihood receiver which purely looks at the likelihoods, the maximum likelihood receiver which purely looks at the likelihoods decides as a 0 as against 1, because the likelihood of 0 is greater than the likelihood of 1. However, the map receiver looks at the a posteriori probabilities and decides a 1 rather than 0. And remember, the maximum a posteriori probability minimizes the probability of error, not the maximum likelihood receiver. So the maximum likelihood receiver, although it is an easy receiver to look at, it is appealing, it does not minimize the probability of error. So the optimal receiver is the map receiver, not the maximum likelihood receiver. So this is, so we have looked at two different kinds of receivers. One is the map receiver and the maximum likelihood receiver, but the maximum likelihood receiver, this does not minimize, but does not minimize the probability this does not minimize the probability of error. So while it is appealing to use the maximum likelihood receiver, it is suboptimal. The map receiver which computes the max, which chooses the symbol with the maximum a posteriori probability, is the optimal receiver, and that uses the Bayes theorem. So the Bayes theorem is very important. In fact, I have to say it's one of the key principles used in digital communication or wireless communication systems. Therefore, it's very important to understand the Bayes theorem and as well as the application of this Bayes theorem in the context of modern wireless and digital communication symbols, because that leads to the optimal receiver which minimizes the probability of error at the receiver. So this module, while the previous module has explained the theoretical or the abstract concept of Bayes theorem, this module has justified this and it has illustrated a very important application of this Bayes theorem or computing this maximum a posteriori or computing these a posteriori probabilities and then choosing the symbol with the maximum a posteriori probability at the receiver in the context of a wireless communication system or the map receiver. So, we will conclude this module here. We will explore other aspects of probability and random variables in subsequent modules. Thank you very much.